Welcome to Fundamentals of Artificial Intelligence. Today we are going to look at uninformed search. Usually in most of the AI techniques that we will explore, we will later look at using domain information, or what is more commonly called heuristic knowledge, which would be under the category of informed search. However, as an introduction to search in graphs, we would love to look at uninformed search first. So what we'll cover today is we will very quickly review problem solving as search, look at what we meant by state spaces. We will then formally introduce graph searching and introduce a generic searching algorithm. Thereafter, we will look at a couple of uninformed search strategies. First, the breadth first search, thereafter the depth first search, iterative deepening, uniform cost search, and then we will look at something called bidirectional search. Let's look at what we meant by problem solving as search. We define a state space that contains all the possible configurations. One or two configurations I have shown you. We would love to define all possible configurations of the relevant objects. We would then look at the initial state, that is, specify one or more states within that state space as situations from which we start. And then we define something called a goal state, one or more states that would be acceptable as solutions to the problem. And of course, we need to specify the operators, a set of rules that describes the actions or operations available. The state space is what is vital for formulating a problem-solving domain as state space search. The state space literally consists of all possible configurations. This is also referred to as the problem space. For the 8 puzzle game that I have shown you little while ago, each tile configuration is a problem state. The 8 puzzle, we should note, has a relatively small space. Okay? There could be problems which would have huge state space, and we would look at how to search it in order to get to a solution. So let's look at problem solving as state space search, and this is the start node which I wanted all of you to take note of. This is as with 9 tiles here, one of them is blank, and you move the blank around to arrive at this goal position. Now, in the last class, we have looked at how these expansions can take place given the 4 operations. We will just look at the complete tree of solution. So, given this state, you could have 3 possibilities of moving the blank. So, the blank is here. You could think of moving the empty to the left. It could come here at this point, or you could think of moving it up to the center, or it could move it to the right. So given the start S, these configurations of tiles are its successor nodes, successors, and we can keep on generating the successors. Like from here we could get more successors by moving the blank to a newer configuration. Like the blank could go up and one could come down, so we could have 2 blank, 1, 8, 6, 7, and 3, 4, 5, and we could have another one which would be like 2, 8, 3, 1, 6, 4. 7 could go this side, and I would have blank here, and I would have 5. So we could generate all the successors from one node. But one thing to note here is that this point here, this node here, is a repetition of what I started with here as my start. So I would avoid getting expansions of these type of successors. Having said that, I would love to get all the successor nodes listed, and then the idea would be to look for a path that takes me through this space of successors to the configuration that I was looking for, and therefore this is line of expansions would be the solution to the problem that I was looking for. Now, if you look at this very closely, we can have a simile here. This can be thought of as a graph, and basically what are we looking for is, given a node, start node of a graph and a goal node G, I am looking for some path that takes me from S to G. So problem solving as state space search can be abstracted to the mathematical problem of finding a path from the start node to the goal node or in a directed graph. So let's take a look at what we mean by graphs and directed graphs before we proceed further into our discussion of problem solving a state space graph. You must have looked at graphs before, but for completeness, so let me put the definition here. A graph G comprises a set V of vertices and a set E of edges. The vertices as can be anything, but is most commonly a collection of letters or numbers. That's the representation. And the set of edges is a set of doubleton subsets of V. That is, E is a group of subset of A, B, where A, B belongs to the vertices and A is not equal to B. Usually the graph is denoted as a two-tuple G, V, E. So if a graph is given and I know its edges, then we say vertices A and B are adjacent, and if there is an edge AB that joins them in the graph, and we call A and B themselves as the endpoints of the edge. Two edges that share a vertex, such as, let's say I have a graph here and I have A here and a B here, and that's one edge. I have another edge A and a C here, that's another edge. So if I have AB and AC, here they are sharing a common node A, and then they are said to be adjacent to each other. So I am more interested here in finding out the path in a graph. Like if you recall, we had this 8 puzzle tile configurations, and where I explored and really got these sort of structure there. As I keep on expanding my nodes at every level, given the 4 operators of the 8 puzzle game to me, and from a given S, as I could arrive at a given G. I am more interested in finding out how did I come from S to G, or get to know what is a path. So the notion of a path in a graph is intuitively very clear, but it's very difficult to pin down it formally. So suppose I have a graph which is a set of vertices and edges, and I have k vertices, so 0, 1, 2, 3 up to k plus 1, not necessarily distinct, and I have edges as E1, E2, so and so forth up to E to the sub k, not necessarily distinct. Now each edge EI is a group of vertices. The alternating sequence that I get of the vertices and edges, starting from the vertex V sub 0 to V sub k, is a path from V sub 0 to V sub k of length k. The length is the number of edges and it's not the number of vertices. So for this path that I have highlighted here, the length of the path is 1, 2, 3 and 4. So here is a 4 length path, and what I wanted to highlight was that this path is made up of edges E1, E2, E3, E4. So alternatively it had vertices, let's call this vertex as VA, VB, VC. So the path from the start to the goal for the given graph would be something like S, E sub 1, V sub A, E sub 2, V sub B, E sub 3, V sub C, E sub 4 and G. So that's the path that's in the given graph. What we are more interested when we were looking at graph search for solutions to given problems is what are called directed graphs or digraphs for short. Here again it has a set of vertices as V, but the set of edges is actually directed edges. So what are directed edges? Directed edges are ordered pair of elements of V. Put another way, if I have a graph of two tuple of V and E is a subset of V cross V, it is a digraph if these pair which I get are ordered pairs. So ordering of pairs in E to give each edge a direction, namely the edge AB goes from A to B. So here is an example of a digraph. I have a set of vertices A, B, C, D and pair of edges AB, AC, BA, CC, DC. So if these pairs are directed at arcs rather than just being edges as in the general graph that I was talking of, then what we have is a digraph. A tree is a connected graph with no cycle. So here if you go back and see the directed graph, here we have a arc that starts at C and comes back to C again. Or if you could see here, we go from A to B and then there is a path from B to A. Such a thing is called a cycle. So in a tree, we have a graph which is connected, but they do not have cycles. And this is something that we'll explore or in the remainder of this lecture. So graph searching for problem solving as state space search is to find a sequence of actions to achieve a goal, or as searching for paths in a directed graph. To solve a problem, we define the underlying search space and then apply a search algorithm. Searching in graphs therefore provides an appropriate abstract model of problem solving independent of the particular domain. And the type of graph we are searching here, one needs to remember, is usually a directed graph. So we are in now position to formalize search in state space. So let's define a state space. A state space for us is actually a graph of vertices and edges where V is the set of nodes and E is the set of arcs. Here when I say nodes, the node may be a simple node or it could be a data structure that contains a state description. It could contain other information such as parent of the node, operator that generated that node from that parent, and other bookkeeping data. And each arc corresponds to an instance of one of the operators. So basically whenever we are talking of formalizing in search in state space, is we are looking at having whole of the state space converted into nodes with each operator giving me some instances that takes me to the other nodes. So finally we end up having such a directed graph, and searching in this directed graph for a path that brings me from S to G is what I mean by getting to the solution. For each arc in such a directed graph has a fixed positive cost associated with it corresponding to the cost of the operator, and each node has a set of successor nodes corresponding to all of the legal operators that can be applied to the source node state. The process of expanding a node means to generate all the successor nodes and add them to their associated arcs. One or more nodes are designated as the start node, and then there is a goal test predicate which is applied to a state to determine if its associated node is a goal node. A solution in such a formal framework is a sequence of operators that is associated with a path in a state space from a start node to a goal node. And the cost of each solution that I am looking for is the sum of the arc costs on the solution path. So, if all the arcs have the same unit cost, then the solution cost is just the length of the solution or the number of steps or the state transitions that's involved. So, state space search under such a scenario is the process of searching through a state space for a solution by making explicit a sufficient portion of an implicit state space graph. Now, one needs to remember that we do not generate the complete graph when we are looking for a solution under this idea of problem solving. We keep on generating the graph as we keep on exploring for the solution. So, it is the process by which you search through a state space by making explicit only a sufficient portion of it, of an implicit state space graph to find a goal node. For large state spaces, it is important to realize that it is not practical to represent the whole space. So, you initially start with just the start node and then expand the start node S, its successors are generated, and those nodes are added to the set V, and the associated arcs are added to the set E. This process continues until a goal node is found. So, instead of having the whole state space graph as it is explicitly generated and then looking for a solution, the idea is to make explicit a sufficient portion of this as I go on expanding for nodes, and every node that I expand answering a question whether that's my goal node. If not, getting its successor nodes and keeping the process continuing. So, state space search is when each node implicitly or explicitly represents a partial solution path. In general, from this node, there are many possible paths that have its partial path as a prefix. So, basically what it means is that when I am doing such a state space as exploration in a directed graph, I have come up to this point and then I keep on expanding beyond. But one needs to remember that whatever I have expanded up to this point, this still forms a part of the path. So, it's still the partial path is still there as a prefix for me. Beyond this, there would be many alternate paths, but this one up to here, if somewhere the goal lies below this node, then up to here this is the partial path that's included already. So, how do we evaluate such search strategies? It's important to realize that we have many such searching techniques that we will discuss, which are uninformed. But how do we evaluate such search strategies? There are four distinct matrices. One, we talk of completeness. Completeness is a guarantee of finding a solution whenever one exists. So, if a solution exists and if your searching technique can find that solution, and the technique is said to be complete. Next, we talk of time complexity, that is how long does it take to find a solution. This is usually measured in terms of the number of nodes that the searching technique expands. Next, we talk of space complexity, how much space is used by the algorithm. This is also usually measured in terms of the maximum size of the nodes list during the search. And then there is a question of whether this search technique is optimal or admissible. If a solution is found, and is it guaranteed to be an optimal one, and that is it the one with the minimum cost? If that guarantee is there for the given searching technique, then it's said to be optimal. We will now look at these searching techniques and then look at the evaluation of these techniques along these four matrices. So what are the important parameters that one needs to really look at before we go into looking at the search techniques and evaluation of them is these three interesting things that needs to be remembered. We talk of a number of successor of any state, the maximum number. That's called the branching factor. Then we talk of the length of a path in the state space is the minimal length, which is the depth of the shallowest goal, or that's D. So we need to understand and something about D and something about B. So if I have a node that's expanded every time into 2 successors, so here my branching factor is 2. If my goal lies here, that's the depth of the minimum length of the path to the shallowest goal, then my D is 3. And I could have a maximum depth which goes on, it could be infinite, and that maximum depth of the state space is M. So given these parameters to me, and given the idea that we could search a directed graph to arrive at from a given and state to a given goal, we look at a graph search procedure. So even before I write the algorithm for the graph search procedure, I would like to highlight that what we literally do is we have the start node S, and we have its successors. Let's call this successors A and B. So we create 2 lists, one called the open and other called the closed, and we first put S in the point where it needs to be expanded. So we create a list called open and we put S in the open list. So we put S here consisting solely of the start node, and then we pick up S for expansion. So we pick up S, and what we want to really check now is that is S as the goal node itself. If not, we generate its successors. So if S is the goal node, we have nothing to do. We must come out and exit. That's what is a check here, by saying that I create a list is called closed, that's initially empty, and then if there is nothing in open, I have to exit with failure. But otherwise I select the first node on open and remove it from open. I take it away from open and put that node in close. Now why do I do that is a way to remember that S has been expanded. So then after that, what I do is I generate the successors of S. So the successors of S here are A and B. So I take A and B and put it in open. And next, when I look for an expansion, I take the node from open, so A comes to me. Now one needs to remember that how I add A, B onto the open list will depend on what criteria do I really follow in order to really arrange this. Is later on we will see that if I am doing a breadth first search, I would see that everything is added to the end of the list. If I am doing a depth first search, I would add it to the beginning of the list. Okay. So basically you create a list called closed that is initially empty, and you take the first node on open, you remove it from open and put it on close, and then if n is goal node, we have nothing to do, we exit it immediately. Else what we do is the following: we expand the node n, generating the set M of its successors. So we install them as successors of n in the open list. So add these members of M to the open list and then expand them further. Now if each member of M is already in G, then we can decide whether we want to redirect its pointers, or if each member is already in close, that means one of the successors is already been expanded, then we can redirect its descendants whatever are there to that pointer, else we will ignore that node to be expanded further. So how do we reorder the list open, and is very, very important to understand, and the type of technique that we will have in the graph search. So they are either according to some arbitrary scheme if it is uninformed search, and according to some heuristic merit if it is a informed search. Today our concentration would be only on looking at arbitrary schemes of arrangement and of the successor nodes in the open list. So we look at uninformed search today, and it's important that we really understand what we mean by uninformed here. Our uninformed search is also called blind search because of the very fact that it does not use any information about the likely direction of the goal nodes. We do not have any idea of the problem domain. So informed search, on the other hand, are also more popularly called the heuristic search, are informed search techniques in the sense that they use information about the domain to try usually head in the general direction of the goal. Informed search methods and uninformed search methods are distinctly different in only either use of no information or use of information about the domain. Few of the uninformed search methods are breadth first search, depth first search, depth limited search, uniform cost, depth first iterative deepening, and bidirectional search. We will look at few of them today. In informed search, we have hill climbing, best first, greedy search, beam search, A and A star, which we will look at in the next lecture. So uninformed search strategies, we do not have information from the problem domain, and that is how we order the nodes in open using some arbitrary screen. Today we will look at this 5 uninformed search techniques: breadth first, depth first, iterative deepening, uniform cost search, and bidirectional search. So what is breadth first search? Let's look at it in more closer terms by using a real graph here. So I have a graph with node A, B, C, D, E, F, G. So what I expand is the shallowest unexpanded node. So the fringe, if you can see by now, is actually a first in first out queue. So new successors all go to the end. So if you recall, we said we will create 2 lists when we are doing graph search, one an open list and another a closed list, and we will keep the start node in open. As we expand, we take A to the closed list and generate the successors of A. So the successors of A that I get, I have B and C. Then the next time I take B for expansion, take B here and keep it in close. And when I get the successors of B, so the successors of B you could see are D and E. So those successors will go to the end of the list. So D and E will come here. So that the next node that I take for expansion is C rather than and D. So this is how the breadth first search works. I expand the shallowest unexpanded node. The fringe is a first in first out queue. That is, the new successors go at the end. So first I check if A is a goal state. If A is not a goal state, I get its successors, which is B and C. So the fringe for me is B, C now. So next I check if B is a goal node. If not, I get its expansion, which is D, E. But then the next node to be expanded is C and not D. That's something that one needs to really understand here when I am doing a breadth first search. And then next node to be expanded becomes D, and so on and so forth. So a few questions that I want to answer about the properties of the breadth first search. The first question is breadth first search complete? We can see that the breadth first search always guarantees that it will reach the goal if the branching is finite. So if I have a state space search to be done starting at a given S to some given G, and I know that this is the state space within which I have all the configurations for those states. And then if branching is finite for this search, so at some point somewhere I will definitely arrive at G. Why would that happen? Intuitively is because I would be expanding everything at every level, and that will guarantee that no state is missed for a finite B, and therefore breadth first search is complete. The number of nodes that we will generate is at this level L it is 1, and if I have B branching at this it is B. At this level it will become B square, then B cubed. So I would have an order of B to the power D. This is the number of nodes we will generate. What about space complexity? Because of the very fact that the breadth first search generates every node at every level, it has to keep all the nodes in it that it had expanded. Okay, so keeps every node in the memory, either in fringe or on a path to the fringe, and therefore the order is of B to the power D. Whether breadth first search is optimal, now this depends. If we guarantee that deeper solutions are less optimal, that is, if step cost is 1, if we assume that every step it just costs 1 and there is no other cost involved, so then it would mean that if I have some solution which is deeper down there, and if I have a solution which is somewhere at a shallower node, I will get the shallower one first, and therefore every time I am guaranteed to get the minimum cost solution. So it is optimal. Next we will look at the depth first search. So you expand the deepest unexpanded node. That's what the clue is for depth first search. And if you have realized by this time, the fringe that I am talking of is last in first out queue. That is, you put successors at the front and those are what is expanded. So you first check if A is a goal node, or if not, you get the successors which are B and C and check if B is goal. If not, you expand that and you have D, E. But the point here that I want to make is D, E would be put in the front of the open list rather than at the end of the list in open. So I have D, I check if D is a goal state, and then I get its successor HI, so I put its successors HI in the front. So here is the queue. If you go back one slide there, I had D which I expanded, and D give me two successors which was H and I. H and I would come to the front of the list rather than to the back of the list. So I check and continue this search. Go on doing I, and then go on doing everything till I expand at every level. So the questions of properties of depth first search: is depth first search complete? You could see from these explanations that a depth first search is not complete, because what can happen is that if I have infinite depth space and I could be stuck in an LA, I could go on expanding down there our line, and nowhere on this line a solution would exist. So first important realization, depth first search is not complete. What about the time complexity of depth first search? If I have M which is the maximum depth and B being the branching factor, then the number of nodes that I need to do is B to the power M. Terrible if M is much larger than D, but if solutions are dense, maybe much faster than breadth first search. But if I have a huge M, then it would be terrible time complexity. In terms of space, as definitely we only need to remember a single path of unexpected and unexplored nodes. So the time complexity is Bm, which is linear, and it may find a non-optimal goal first, but in terms of optimality, it could be possible intuitively that there are goals here somewhere at lower levels, which will definitely be missed by any depth first search technique. So it is not an optimal search technique. Next we come to a modification of depth first search, which is depth limited search. To avoid the infinite depth problem that I was showing you in the previous slide of depth first search, we can decide to only search until a depth L. That is, we don't expand beyond depth L. But then what will happen is that if we keep that limit L, we may have a goal which lies just little well beyond L, and we will never be able to find this goal. So a better idea would be that what if I keep on changing L and iteratively keep on increasing L. So this is the idea of the next search technique that we will discuss, called the iterative deepening search. So iterative deepening search, I looked at level 0 first, then I look at level 1 for the goal, then level 2, level 3, so on and so forth. So the idea of iterative deepening is, let me repeat it. So I start with level 1, then I go to level 2, level 3, level 4. So the idea is that I take this level, I did not find things here, so I thought of doing a little bit more deeper level. I did not find things there, I may think of going even down. I did not find things there, I may think of going even down. So this is what is iterative deepening search, where I increase the depth bond at every iteration. So properties of iterative deepening, very quickly, it is complete. The order of time complexity is O b to the power d, space is O b d, and it is optimal if step cost is 1 or increasing function of depth. Next, we concentrate on something called the uniform cost search. If you remember, breadth first is optimal, but this is optimal if step cost is only optimal if step cost is increasing with depth, that is, it remains constant. Can we guarantee optimally for any step cost? For that, we look at something called the uniform cost search. We expand node with the smallest path cost. So here is a small graph. This is a graph to find a path from S to G. So here is my start and here is my goal. So first, when I expand S, I have then its successors A, B and C. But the question is, which one do I expand next? As when I look at this, I could see that the cost to A was 1, the cost to B was 5, and the cost to C was 15. So I would rather expand the node with the smallest cost. So I expand A. So my next expansion is of A, where I get to G, and I know that the cost is A to G is 10 plus 1 here. So 10 plus 1, 11. That's what I mark at G. And the other nodes that I have is B with a cost of 5 already there, and C with a cost of 15 already from the previous expansion. So next, which node to expand? If I ask the same question, then I go to expand the node with the smallest path, and therefore I go and expand B. So once I expand B, I have here on this marked B to G, so I get G, but the path cost is 5 and 5, that makes 10, so the G cost is 10, and here it was 11, and now C 15. So the next node that I want to expand is this node, and that when I see that, I know that this is a goal node and I stop, but I pick up this. So this path that I got is the path which is with the minimum cost. So uniform cost search, implementation wise, the fringe that I am looking for is definitely Q, but then they are ordered by the path cost. So this is equivalent to breadth first if all step costs were all equal. The question is whether they are complete. Yes, they are, and the number of nodes with path cost is always less than equal to cost of optimal cost. Number of nodes on path with path cost is greater than equal to cost of optimal cost. And whether it is optimal or not, yes, for any step cost, the uniform cost search is an optimal graph search technique. So let us now look back again and illustrate these uninformed search strategies that we have learned today. So we have looked at breadth first search, we have looked at depth first search, we have looked at iterative deepening, and we have looked at uniform cost search. So here is a small graph that I want all of you to look at, and over this we will try to explain and illustrate all of these search strategies. So here is S, A, B, C its successors, D, E, then and B successor G and C. So I have put the cost of every path in red there besides each of the arcs. So first let's look at breadth first search. So if you are looking at breadth first search here, we know that we start with S0, here S in that list, and then we generate its successors. So we put this, so in terms of the algorithm that I was talking of, we call this node list is open and we call this node list closed. So we create a list called closed and we create a list called open. In open we have S0 to start with, and we pick up S0, take S0 here to close and get its successors into open list. So I have successors A, B and C, so I put A, B and C in that list. Then the next node that I expand is of course A, and therefore I move A here to this, and I have now B, C, but because it is a breadth first search, therefore I include its successors D, E and G to the end of the list. So here is where D, E and G comes to the end of the list. And the next node that is taken up for expansion is B, and its successors, which is G, is added to the end of the list here. So on and so forth. So finally I have expanded E, and then the next node that I get is this E. So I have a solution because G is the goal node. So the solution path that I am talking of is very simple, S to A to G. So that's the solution, and the cost of the solution is 3 plus 15 equal to 18. Number of nodes expanded including the goal node is that we could expand 1, 2, 3, 4, 5, 6, 7 nodes. So we had expanded 7 nodes including the goal node. The depth first search is what we will try to expand now. So in this we take S, put it in this list, and next we take the successors which are A, B and C and put it in the list called open, take S0 to close. Next we take A3 for expansion, its successors D, E and G. Now this is something that we need to take care of. We put it in the beginning of the list here. So as we put it in the beginning of the list, the fringe movement is along this line. So the next thing that comes to be expanded is D, and that is how it happens. And the solution path that I get here are also is SAG, the same solution path. But what is more interesting is, because I took this path and then this was the maximum depth, I came back and expanded E again, and then I came back and got G. So the number of nodes that I expand is only 5, including the goal node is only 5. This is depth first search. Next, we just highlight one idea of simultaneously searching from the forward from S and backward from G. So stop when both meet. So we have a node S here and we have a G here. We are looking for a solution from S to G. So you keep on expanding and looking for a fringe. So the fringe keeps on coming here, and from G you keep on going in this side, and we stop when these two fringes come and meet. So only point that needs to be now discussed or understood is what does it mean to search from backwards from G. it basically means that we need to specify the predecessors of G. At times this could be difficult, like in chess, what is the predecessor of checkmate? What if there are multiple goal states? There is a problem. And what if there is only one goal test, no explicit list? So what do I do? So basically a bidirectional search is an alternate searching from the start state towards the goal and from the goal towards the start. You stop when the frontiers intersect. Works well only when there are unique start and goal states. Requires the ability to generate predecessor states. That's something very important and can sometimes lead to finding a solution more quickly. Here are the time and space complexities. So only thing that is important to realize when I am doing uninformed search over graphs for problem solving as state space search is failure to detect repeated states. Because if I have some failure to detect repeated states, this can turn a linear problem into an exponential one. And there are two interesting solutions. In the first method, which is suboptimal but very practical, is I do not create paths containing cycles. This is what I highlighted in the beginning. And in the second method, the idea is to never generate a state which is generated before. So, but then this would require that you keep track of all possible states. So it uses a lot of memory. For a very simple game like 8 puzzle, you would require something like factorial 9 states in such a case. But then, and these solutions work very well because then you do not create exponential problems of the state space. So this is all that we have in uninformed search. In the next class, we will look at information from the problem domain being used to direct these searches, which are more commonly called the heuristic search techniques. Thank you.